Welcome to CEC lectures. Myself Dr. Priti Jagwani. I am an associate professor from the Department of Computer Science, Arabic College, University of Delhi. So in my previous lecture, we have looked into what actually alpha beta pruning is and what are going to be the necessary steps for this alpha beta pruning. Now we are going to take this alpha beta pruning in a step by step manner by taking a complete example. So here is kind of the tree which is going to be the first example of Earth. So we have seen this is kind of an we can say it's a familiar tree because we have seen this tree in our previous lecture also. So the first step, if you can see, was the initialization of the alpha and beta value. So we'll start from the top as we go in the kind of depth first search manner. So in depth first search manner, please recall we start from the top and then we go in deeper till we have the way to go deep down into the tree, and then we kind of start the backtracking. So first, if we look into the first step, so the first step was about the initialization, which says we need to set up the initial values. So the initial values are being set up for the node A, where your alpha is equals to minus infinity and beta is equals to plus infinity. Please recall, when I am saying alpha and beta, these are the worst possible scores for maximizer and minimizer. Now first of all, in the first step we need to take care of the first move. We define alpha as minus infinity, beta as plus infinity. Now in order to prune the nodes or in order to prune the branches, what is the condition? Please recall, I have already told you in the last lecture that when your alpha is going to be greater than or equals to beta, then only we are going to prune the node. So here at this juncture, this is not the situation because alpha is minus infinity and beta is plus infinity. So we are not going to prune anything because the initial value of alpha is less than beta. So now you kind of understand the rationale behind we can say keeping the value of alpha as minus infinity and keeping the value of beta as kind of the plus infinity. Now we can say it is the turn for kind of the max node. So because that is the first node which is at the node A, that is going to be evaluated. Now alpha with minus infinity, beta with plus infinity, no pruning, and the turn is of max node. Now please recall the second step which we have seen in our previous lecture, which was kind of evaluation of this max node. So this kind of we are going to do, but the point is we will calculate we will prune the node only if your alpha is greater than equals to beta. We did not prune the initial one, now it is turns for max. So we will calculate the value of alpha at the node D, because the value of alpha at node D, the value of alpha will be max of 2, 3. Now why we are saying 2, 3? Because when we start in the depth first manner, so here you can see in the figure. So we have started in the depth first manner. So from A we came to B, from B we came to D, and at D now it is the kind of time for the evaluation. So D, if you can see the ply of this D, E, F and G, this is actually a max ply. Now max ply, if we see and we need to calculate the value at node D, value at node D by the virtue of minimax algorithm is going to be the maximum value of 2, 3, which is going to be 3. Now at the max ply we are kind of we need to update the value of alpha, and at the min ply we are going to update the value of beta. This is the rule which we need to kind of take care of. Now at D, which is the max ply, we have the value as 3, which is the maximum of 2, 3. Now we have alpha as the max of the alpha value. Originally it was minus infinity and the node value which is 3. So alpha is equals to the max of minus infinity or 3. So definitely it is going to be 3. So here we are going to update the alpha as 3, and this you can see in in the screen shown here, that alpha is being updated to 3. So, we have started from in the left first manner A, B, D, evaluated the node value of the D, and if we need to or if it is coming more than the current value of the alpha, we will update alpha at the max ply, we will update beta at the min ply. So, this is going to be kind of the scene. So, at node D, the value of alpha is going to be the max of 2 comma 3 or kind of 3 comma minus infinity. Now, it is the turn of the node B, which is one level above the D, and the ply is the min ply. So, that means the value of alpha beta at node B will be minimum of 3 comma infinity. Therefore, alpha will be minus infinity and beta will be 3 at node B. Now, these values are actually being kind of passed on to the next values, or we can say the next level up. So, the algorithm will pass the values of alpha as minus infinity, because at min we are not going to update the values of alpha, and beta will be updated at the min ply, which is being updated to 3 to the next successor of the node B, which is the node E. Now, how node E is going to be the successor? Because this is the manner in which your depth first search is going to work on. So, at D we updated alpha because that is the max ply, at B we updated the beta because that is the min ply, and now these values are going to be kind of passed on to the successor, which is the node E. Now, at node E you can see that that is the turn for max. Therefore, we will search for max at node E, and the value of alpha is minus infinity will be compared with 5, which is max of minus infinity and 5. So, it is going to be 5. So, thus at node E the alpha is going to be 5, and so is your kind of beta, we can say. Now, alpha is 5 and beta is also 5. Now, please recall the rule to kind of prune the condition. If alpha is greater than equals to beta, the condition is of pruning. So, we are going to prune the right successor of the node E, because till this point we have just evaluated the left successor, and right successor we need not to evaluate, because the value of node E is kind of value of node E becomes 5. Now, in the next step the algorithm again comes from node B to node A, which is the topmost node. The alpha of node A is actually, that is the kind of max ply, if you recall. The alpha of node A is changed to the max value of max minus infinity 3, which is again 3. So, now the alpha and beta at node A are 3 and plus infinity, and this will be transmitted to the node C, which is on the right hand side, or we can say which is the right child of the node A, and the same values will be transferred to the node F. So, if you want to see the structure in order to kind of recall it. So, here we have evaluated the node D, updated the value of alpha. At B we have updated the value of beta. Again at A we have checked for alpha, because that is the max ply, that is being passed on to C. But before evaluating the C, we need to evaluate the children. So, we come to the F node, and in this situation the algorithm, when it is kind of transmitting the values to node C, and the same values are transferred to node F. Now, value of alpha will be compared to the left branch, which is 0 at node F, and now max of 0 comma 3 will be 3, and now then it is compared with the right child, which is 1, and max of 3 comma 1 is 3. So, still your alpha is 3, because there is no condition through which you can kind of update the alpha, because alpha has to be the max of the kind of the current value of the alpha and the node value. So, the current value of alpha is 3, the node value is 1, because max of 0 comma 1 is 1. So, the alpha is still 3 and the node value of f is 1. So, this is what is the situation presently is. So, afterward this node f will pass the node value 1 to C and compare it to the beta value at C. But at C, please recall, the turn is for min, it is not the max turns. So, minimum of plus infinity or 1 is going to be 1. Now, at node C, we have alpha is equals to 3, beta is equals to 1 and alpha is greater than beta, which again satisfies the pruning condition. We have already pruned the right child of the node E, and now here we have one more pruning condition, because alpha is 3, beta is 1 at node C. So, the successor of the node C, which is nothing but G, will be pruned, and please pay attention here that the algorithm is not going to calculate the whole subtree G. So, in totality, if you need to see how this alpha beta pruning what all we have gained from here. So, this is kind of right child of E is not to be evaluated, also the whole the G part or the node G and its children subsequently are not to be kind of evaluated. So, we have kind of in this, even in this smaller tree, we have gained I can say a substantial efficiency using this pruning. Now, C will return to its node value to A, and then A will calculate max of 1 comma 3, which results in 3. So, finally, the result is going to be 3 at the node A, that is there. So, the tree which we have just represent is has represented the final tree that has nodes that are computed and the nodes which are not even computed. So, therefore, in this example the optimal value of the maximizer is going to be 3, and so this optimal value of maximizer can be kind of even we can say calculated with the help of minimax algorithm. But in minimax algorithm, if we are not going to optimize that using this alpha beta pruning technique, whatever nodes we have pruned, which is E, right child of the E, and then we have the right child of the C, which is the G node complete and its children obviously, are not going to be pruned if we apply simple minimax algorithm here. Moving further, let us look on to the kind of one more example quickly. So, we have alpha as plus infinity, alpha as minus infinity, beta as plus infinity at the max node, which is the A, and then at the D, which is the max ply, we are going to look into the max, which is the max of 1 comma 4. So, value of alpha is being updated as 4, and now kind of we send the values to B, and B is going to send the values to E. Let us see how it is happening. So, initially when we say maximizer node A, that sets alpha to negative infinity, beta to positive infinity, assuming that node A selects node B which inherits those values. Obviously, that is kind of we can say the depth first manner. Node B, which is also a maximizer, picks node D. At D, the maximizer chooses the max value of 1 and 4, which is 4, updates its alpha. Upon returning to beta, which is the minimizer, it compares its current beta with D's alpha value in order to see whether we need to go for evaluation or we need to prune. So, if the D's alpha is smaller, B's beta value get updated. In our example which we have just taken, B's beta gets updated since D's alpha value is smaller. So, B's beta value is also updated to 4. Now, the node B, which selects the node E and then passes down its current alpha and beta values to node E. So, node E inherits the alpha value of negative infinity and beta value of plus 4 from the node above it as the maximizer, because E is at the kind of maximizing position, as you can see in this figure, E is at maximizing. So, E as at the maximizing position, or E as the maximizer, explore its left leaf node which holds a value of 5. 5 is greater than negative infinity, E's alpha gets updated. Given that alpha is greater than beta, the other leaf node in E is going to be, is unnecessary. So, is unnecessary to explore. So, it will get pruned. Now, right child of the B, right child of the E we have pruned. Now, at node B, it compares its beta value with node E's alpha. If E's alpha value is lesser than B's beta, updates with E's alpha. However, if E's alpha is greater than B's beta remains unchanged. Now, what is the scenario in our example? In our example, since B's beta is not greater than E's alpha, so B's beta value remains the same, and we need now from here in the depth first manner we need to return to the node A. So, its alpha value is updates with B's beta values because B's beta is greater than A's alpha. So, here at the node A you have alpha equals to 4, beta is equals to infinity, and we have already seen that the branch which is striked out by the 2 red marks is actually the one which is being kind of pruned. So, we have completely pruned this branch. Now, at node A we still need to kind of look into the right side or right child of the node in this tree. The maximizer's alpha becomes 4, ensuring a value of 4 or higher. A then explore its right child which is at node kind of we can say C. At C the alpha is 4, beta is positive infinity. C then chooses its left child which is F. Node F inherits the alpha value 4 and beta value positive infinity from its parent node which is C. F's left child yields 0 because that is the value, updating F's alpha to 4, and also F's right child yields 1. Although F can achieve 1, alpha remains 4. C receives 1 from F which makes the beta as 1. As alpha is greater than beta, the entire subtree of the node G gets pruned. This pruning logic actually ensures that as C is guaranteed 1 or less, it is irrational for A to choose C over B, whereas A is already having a guarantee of kind of 4. So, in kind of totality, if you look into, we have pruned as similar to that of our previous example, we have pruned the right child of the node E as you can see here, and also the whole right child or right I can say sub tree of the node C which is the total G part. So, yes, we can kind of improve our speed and efficiency both by using this alpha beta pruning. Now, if we need to look into what all are the advantages in totality of this alpha beta pruning. So, the first which comes into our mind is about definitely about improved efficiency. Thus, by pruning unnecessary branches, alpha beta pruning significantly reduces the amount of computation. Also, I can say space complexity is also kind of can be done better. The algorithm can focus on evaluating only the most relevant parts which are actually contributing to the outcome, making decision making much faster. So, improved efficiency obviously is one kind of the advantage. With this improved efficiency there comes reduced time complexity, because without pruning the minimax algorithm we have seen is as the complexity of order of b to the power d, or we can say b to the power m, whatever variable you choose here, where b represents the branching factor, number of possible moves, d or m is the depth of the tree. With alpha beta pruning, the time complexity can be reduced to order of b to the power d by 2 in the best case. So, that means I can say half depth. It is in the best case. So, enabling our AI agent to explore the deeper levels of the tree much more efficiently. Then comes the next advantage, which is scalability. So, as AI applications become more complex and requires deeper search trees, for example, in case of Go or chess, this optimization technique of alpha beta pruning makes exploring these large search spaces feasible. The ability to prune unnecessary branches means that AI systems can handle more complex decision making tasks in real time. Now, we have seen that we have scalability, we have reduced time complexity, we have improved efficiency also, but here it is very important to name some of the real world applications in which this alpha beta pruning is actually used. So, this alpha beta pruning is widely used in AI applications where decision tree needs to be explored efficiently. This is the use case scenario. What are actually the real life applications? So, the real life applications of alpha beta pruning, first is game AI. In strategic games like chess, we have checkers or Go. Alpha beta pruning becomes crucial for enabling the AI to evaluate millions of possible moves in real time, because you imagine the number of possible moves in case of the chess or in case of checkers. Games like Stockfish, again it is related to chess, and AlphaGo, which is Go, uses alpha beta pruning as their core component of the decision making algorithms, enable them to compete with human players at the highest level. It is not only the game AI in which this alpha beta pruning is going to be used. Apart from this, we have autonomous systems and robotics also, because decision trees are used frequently in robotics automation for real time decisions on movement, navigation and task execution. Alpha beta pruning helps in quickly evaluating different paths and strategies through robots, which help them to respond faster in a dynamic environment. More on the go, we have models on finance and optimization. So, decision trees is also used in financial forecasting, portfolio optimization and supply chain management through AI systems, especially in evaluating different scenarios and making predictions. To make more timely decisions, these systems could use alpha beta pruning in order to process the large data sets. Then we have looking into the advantages of alpha beta pruning was one side of the coin. The another one is limitations of alpha beta pruning. So, alpha beta pruning, although it is kind of an very welcoming optimization step, optimization technique, or we can say it is kind of an powerful tool, it is also having some of the limitations. So, the first limitation is branching factor. The effectiveness of alpha beta pruning depends on the branching factor of the game tree. If the branching factor is very high, pruning may not reduce the computation enough to improve performance significantly. So, that that kind of we can say trade off is obviously going to be there. And also one assumption which I have stated when I was teaching you about the introduction of the alpha beta pruning, that it assumes that both the players are actually playing optimally, which may not always be true in the real world situation, especially when there human players are involved. They may not play optimally, but this is the assumption through which your alpha beta pruning is kind of we can say going, that it assumes the optimal play. Real world examples, we have seen that we have AlphaGo and the this kind of some chess engines. So, two prominent examples of alpha beta pruning already in action are AlphaGo and some modern chess engines. So, AlphaGo, this is the AI developed by DeepMind, used a combination of Monte Carlo search trees, which is obviously is not in the kind of a scope of this course. Along with Monte Carlo search trees MCTS, the alpha beta pruning is also used to evaluate possible moves in the game of Go. By pruning unnecessary branches and focusing on the most promising moves, this AlphaGo was able to defeat even the world champions, we can say. Chess engines like Stockfish and uses this alpha beta pruning to evaluate millions of potential moves per second. This allows them to calculate the best possible moves in real time, making them capable of competing with and defeating top human players. So, in this lecture we have looked into the complete working with the help of couple of examples of alpha beta pruning, and we have also seen the real life world examples, the advantages of alpha beta pruning, also the other side of the coin, which is the disadvantages. So, alpha beta pruning, we can say it is an essential optimization technique for AI decision making algorithms. By significantly reducing the number of nodes that needs to be evaluated, this alpha beta pruning makes complex decision making processes more efficient and feasible, even for, we can say, large scale problems. So, whether in game playing, AI, robotics or optimization systems, alpha beta pruning is a cornerstone of AI algorithm that requires fast and accurate decision making. That is all from my side in this lecture. Here is a list of references which is being used for the preparation. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.